So while explaining the stabilization of austenite during binary transmission, I used one sentence known as incomplete reaction phenomena. Okay, that means that the bainite when it is transforming from the austenite, it ceases to form upon the sufficient enrichment of carbon in austenite, right. So incomplete bainite reaction or incomplete reaction phenomena. So that is actually governed thermodynamically, which is actually shown in this slide. I will explain as well. So suppose if you are cooling an two-phase microstructure ferrite on the austenite to a temperature say around, in this case, 400 degrees centigrade, and you form bainite without the formation of cementite, right. So it will be only bainitic ferrite, and when during this formation the austenite is getting enriched in carbon, but upon say some moment upon a critical enrichment level, the reaction stops. The bainite reaction, bainite transmission, bainite formation from austenite does not continue till the end. Okay. So when the austenite is enriched to a critical limit, the bainite reaction stops. Okay. So that is why the bainite transmission is known as incomplete reaction phenomena, and this is actually the critical carbon concentration upon which at this critical carbon concentration the reaction ceases to exist. That critical carbon concentration is defined by here is a T0, which is thermodynamically known as allotropic phase boundary. So what happens here again, so this is a phase diagram I superimposed to a heat treatment thermal cycle. So what we are doing it, we are taking it to intercritical temperature, right. So this is a temperature, for example here, say this is your total carbon concentration, I already explained, say 0.2, and we are taking it to phase regions where both ferrite and austenite is coexisting, and we form a microstructure, say for example 60% ferrite and 40% austenite, and your 40% austenite carbon concentration is given by this point, right. That will be higher than your bulk carbon concentration, right, 0.2. Now we are cooling the microstructure of 60-40 for example, or even say 50-50, no problem. We are cooling this austenite to temperature regions of the isothermal bainitic holding, and at this holding, and we are forming bainite without cementite formation, and during this process the carbon is pushed towards the untransformed austenite, right. Until what point? So until the point is known as T0 or the allotropic phase boundary. Okay. So allotropic phase boundary is defined by the definition is the free energy of ferrite and austenite is same and for a given carbon concentration. Okay. So we will explain in previous slides, for example the point at which the free energies, the Gibbs energies of ferrite and austenite becomes equal at a given carbon concentration. Okay. So that carbon concentration is known as T0 or allotropic phase boundary. Okay. Say for example at a temperature T equal T1, at this temperature the point at which the both ferrite and austenite would have a same carbon concentration. That point is known as T0 or allotropic phase boundary. So until the carbon concentration reaches that point, okay, you would have a bainitic transmission. So once your austenite carbon concentration reaches the T0 carbon, the carbon concentration at which both ferrite and austenite will have a same Gibbs energy, okay, and your transmission ceases. That means that no more transmission of austenite to bainite, bainitic ferrite. Okay. So that is the reason we stabilize austenite during this bainite transmission, and the critical point is here is we need to enrich. Okay. So if you enrich the remaining austenite with carbon, you reach T0 much earlier than if you form cementite. So you would significantly, if you retain the austenite, because of this incomplete reaction phenomena driven by the enrichment of carbon in austenite by the suppression of cementite, and this austenite subsequently when you cool to room temperature, right, and yeah, you cannot transform to martensite fully because of decreasing in MF temperatures below say MF temperatures below room temperature. Okay, and so this is the thermodynamics of the stabilization graphite and austenite. So it is driven by the incomplete reaction phenomena of bainite, and austenite ceases to transform to bainite upon enrichment to T0 carbon concentration. Okay. To summarize, okay, so the formation of carbide free bainite is very critical for trip steel microstructure. So carbide free bainite is nothing but supersaturated ferrite. Okay, so there is no cementite. So you form ferrite with slightly higher carbon concentration, you suppress cementite. So role of silicon aluminum phosphorus is very critical. Okay, so because silicon aluminum suppresses cementite formation and also as well as phosphorus if you add. And because of the suppression of cementite, you can enrich the austenite. The carbon concentration of austenite reaches to say T0 carbon concentration, and your austenite cannot transform to bainite or any diffusional transformation. So only diffusionless transformation is possible. But yeah, because of MF temperature decrease, you would stabilize retained austenite at room temperature. Okay, so. So all these three are important. You have bainite, it's nothing but supersaturated bainitic ferrite, okay, in trip steel, and silicon aluminum and phosphorus additions are extremely important to suppress cementite formation, and the concept of T0, the allotropic phase boundary, which is actually determines the cessation of the bainitic formation from the austenite, lead to stabilization of retained austenite in trip steel microstructure. Okay, I hope it is clear for you how we stabilize this beautiful 3-phase microstructure in trip steel. These three are the critical points you need to remember. So we will move on to the next generation, next microstructure of advanced high-strength steel. So we looked at DP and TRIP, and the third advanced high-strength steels is hot stamping steels. Okay. So before going to the microstructure of hot stamping microstructure, anyway it is very simple. It is martensitic after hot stamping. Okay. So if you take a martensitic microstructure, and if you want to deform at room temperature, it is extremely hard. Okay. So you need to have enormous amount of mill load to deform the martensitic microstructure. Okay. But no, somehow we can overcome the problem of ductility by starting a simple ferritic paletic microstructure. Okay, so ferritic microstructures are easy to deform compared to martensitic microstructure. But yeah, if you use a conventional ferritic microstructure, as I showed you in the Banana diagram, your strength cannot be increased to beyond certain megapascals. For example, a mild steel or HSLA steel, if you look at it, your UTS would be around say 400, 350 to 400 megapascal in conventional HSLA or mild steel, even less than that. So we take the ferritic paletic microstructure, and we heat it up to temperatures where we have fully austenitic microstructures. Okay. In hot stamping case, we do not deform at room temperature, but we will deform in the austenitic condition. Okay. So we will take it, we heat up the sheets to high temperatures, and we transform the microstructure into fully austenitic regions. So what we do in again the eutectite phase diagram, eutectite regions of the iron carbon phase diagram. So we have austenite, and this is the intercritical region we saw in the previous slides. Okay, and this temperature and carbon. So we heat up microstructure containing say ferritic paletic to a single phase austenitic region, and then we do a deformation. Okay. So why do what advantage you would gain by doing by carrying out deformation austenitic region? Because material softens significantly when the temperature increases. Say this slide, I showed you a graph here, one of our work, which shows Young's modulus and yield stress as a function of temperature. So what is yield stress here? It is the onset of plastic deformation, right? The yield stressed above which the plastic deformation triggers or plastic deformation initiates. If you look at this graph, okay, so by increasing temperature, the yield stress decreases significantly. So you will have a significant high yield stress if you have a precipitation hardened material, okay, and if you are increasing temperature, say at around 1000 degrees centigrade, where you have a fully austenitic microstructure, so the yield stress is not even about 50 megapascal. Okay. So similarly, the Young's modulus would also decrease significantly as a function of temperature. Okay. So we can take an advantage of softening of material at elevated temperature, and by combining the phase transformation upon deformation, and we can significantly increase the strength after deformation. So what we do in this structure? So you can start with a very simple ferritic bainitic microstructure. Okay, you take it to an austenitic region and you deform it to whatever shape you want. Okay, and then you cool it to room temperature, and during this cooling you convert the entire austenite microstructure into a martensitic microstructure. Okay. So you form it at a very soft stage. You see that yield stress is not even 100 megapascal. Okay. So you can deform it very easily at austenitic regions, okay, and then subsequently quench to room temperature. So your component microstructure after the forming would entirely become martensitic. Then the strength of the component would increase significantly because of the formation of martensite after quenching. Okay. So the advantage of this hot forming is reduction in forming load, because the material ductility increases significantly, it softens significantly at high temperatures, and then you transform the austenitic microstructure upon forming to martensitic, and during this process material gains strength significantly. You can reach a strength of 1400 to 1500 megapascal. Okay. And the other added advantage is because of the plastic deformation, the phase transformation and the deformation at high temperature, and both combined would also lead to decreasing in spring back. What is spring back? Again, to elastic recovery after forming. Okay, that will also significantly reduce, and because of the high temperature deformation coupled with the phase transformation of martensite. Okay. Now the critical metallurgical factor that can influence the hot forming process is your phase transformation temperatures. Okay. Generally it is advised to do hot forming or the forming or stamping in the austenitic region, because if you are taking it to intercritical region, there are all complexities in terms of microstructure, and there will be two phases if it is present, and there will be stress partitioning between the ferrite and austenite, because they both have different carbon concentration, the strength will be different. So it is generally not advisable to stamp or form at intercritical region. So you need to take it to a fully austenitic region where you have single phase microstructure, you will have uniform carbon concentration or alloying element concentration, and then you deform it or whatever rate, as well as whatever amount degree of deformation, and subsequently you quench it to room temperature. Generally it is done in press. So you press it up, you have to make a component, and you hold the component in press and cool it to room temperature. Okay. And during this process the component microstructure transforms completely to martensitic microstructure, and during this process the strength increases significantly, and because of high temperature deformation and the phase transformation of martensite, formation of martensite, you also control the spring back significantly. Okay. And the actual thermal cycle what you use is shown like this. So it's shown in this graph. The critical factors I will explain in terms of getting the final microstructure. So you start with a ferritic bainitic microstructure. Okay. So, the the composition of the hot stamping steel is also similar to what you have in in ideal phase steel typical, but some special alloying elements that are added in hot stamping steel. One such alloying element is boron. The role of boron in hardenability already explained. I will also explain again for your convenience during explaining this slide. So, you start with ferritic palladic microstructure containing slight some amount of boron as well. It is not more than 30 or 40 ppm. Okay. And the microstructure, the other compositions are similar to dual phase steel microstructure composition. So, you will have manganese, you will have silicon some amount and chromium. Okay. So, you may also have of course carbon, say 0.2 is about 1 to 1.5, silicon say 0.5. This steel does not have as much silicon as in trip steel. Only in trip steel we have a high amount of silicon in silicon based strip steel or aluminum, and chromium is about 0.5 and you can also go high. The important alloying element in hot stamping steel is boron. Okay. So, boron we have about 30 to 40 ppm. Okay. So, now we take the microstructure of simple ferritic palladic microstructure and you take it to a fully austenitic region. So, you heat it up, you form fully austenitic grains and then you deform it, okay, whatever shape you want to do that, and then you after deformation, after forming, you cool to room temperature. For that, what do you need to do? The cooling rates would be above the critical cooling rate, right. So, you have a CCD diagram superimposed, and so this is your bainite formation nose. So, you have a bainitic phase, and this is ferrite start, and this is pallite start, pallite end, and you will have a martensite the MS line somewhere over here. And if you are cooling here with a slightly slower cooling rate, then the microstructure would also form into bainite. So, we should avoid that. So, we need to make sure that the steel is cooled to above the critical cooling rate needed for martensite formation. So, your austenite would completely transform to martensitic microstructure. Okay. So, as I had explained during in CCD diagram, in order to get a complete martensitic microstructure, we need to increase the hardenability of the steel significantly. So, what do you mean by hardenability? So, we need to push the CCD diagram as much right side as possible. Okay. Suppose if this line is somewhere over here, that is not good, right. So, we need to, then you may end up transforming austenite into the other high temperature products, say for example pallite or bainite. So, in order to get complete martensitic microstructure, so we will have to have critical cooling rate. So, yeah, for example decrease to some extent, so that even at slower cooling rate or cooling rate generally achievable in a die quenching can give to a fully martensitic microstructure. So, one way of obtaining this is to move these CCD diagrams towards right side, right, and the one alloying element that can do effectively is boron. Okay. So, boron can increase the hardenability or decrease the cooling rate needed for martensite formation significantly. So, how it does? Boron actually when in austenitic microstructure, when you add boron, so boron readily segregates to the grain boundaries of austenite at this temperature range, for example. The moment boron segregates to the grain boundary, okay, when you are cooling this austenite to room temperature, for example here in this case, the nucleation of ferrite is retarded. Okay. Say even if you form a pallite or bainite, you need to nucleate a ferritic cloth. Okay. The solubility of boron in ferrite is also very low. Okay. And if a ferrite has to nucleate, and boron atoms has to be pushed out. Okay. Otherwise ferrite cannot nucleate, right. So, if the boron atoms segregate the grain boundary, it is very difficult for boron atoms to move away from the grain boundary, because grain boundaries are the most energetically favorable locations for the boron atoms. The moment boron atoms comes to grain boundary, the nucleation of ferrite becomes sluggish, okay, because if a ferrite has to nucleate, it has to push the boron atoms from the grain boundaries, right, which is not possible energetically. thermodynamically or even kinetically you can say. So the nucleation of ferrite is retarded. What will happen then if nucleation of ferrite is retarded? This austenite remains as austenite, right? And if the austenite remains as an austenite and subsequently if you cool back, if you cool that to microstructure, there is no partitioning. Okay, so it's a simple austenitic microstructure. If ferrite nucleation is retarded, the austenite can fully transform into martensite, right? So because of the retardation, the austenite stays as austenite, and subsequently when you cool to room temperature, the austenite transforms to martensite. Okay, it's clear. So the role of boron is extremely critical to achieve the martensitic microstructure in hot stamping steel, because of the addition of boron, and we can form martensite in reasonably slow cooling rates. So, and the CCD diagram is moved towards right, thereby decreasing the cooling rate required for martensite formation. And why is it happening? Because of the segregation of boron to the grain boundaries, and due to the segregation of boron, the ferrite nucleation is retarded, and thereby the austenite can be transformed to a fully martensitic microstructure. So we start with a simple ferritic bainitic microstructure, conventional microstructure, say for example in a mild steel, and we take it to austenitization and deform it and form whatever way you want, and then cool it to room temperature. Okay, you get a component, for example say deep drawn cup full of martensitic microstructure, a complete martensitic microstructure. So you start with a very soft, reasonably soft material, and end up a fully martensitic microstructure with the strength level of say 1400 megapascal to say 1500 megapascal. Okay. So now again, boron is also it is not really a detrimental element in terms of weldability, but role of diffusion of boron to grain boundaries can significantly change the diffusion of subsequent or other alloying elements. It may not really detrimental for the weldability, but it can affect the segregation of other alloying elements, say for example phosphorus segregation during welding. So it is really important to look at the role of boron as well during welding, which we will see in subsequent classes. Okay. So this is also the effect I already showed you, how the boron addition affects the CCD diagrams. So this diagram shows the hot stamping steel without any boron. You see the critical cooling rates is somewhat, it's even more than 100 Kelvin centigrade per second. So somewhere over here, sorry. Okay. So even if you cool it 100 Kelvin per 100 centigrade per second, you will still form the high temperature products like ferrite and in this case bainite. Okay. So by adding 30 ppm of boron, you already see critical cooling rates needed for martensite decreases significantly. Say previous without boron, even at 100 centigrade per second, you formed a significant amount of ferrite and bainite. Whereas just by adding 30 ppm of boron, you see that at 100 Kelvin per second, you have a fully martensitic microstructure. Okay, so even if you cool it, say for example critical cooling rate of 80 Kelvin per second, you may still get a martensitic microstructure. So you don't change the composition much, you have all of them similar like aluminum, say chromium, manganese 1.17, silicon, okay, and carbon of 0.23. It is the same as a previous case, okay, but we just add about 30 ppm of boron, and that can change the critical cooling rate significantly, because the boron decorates the grain boundary, and because of that you suppress the ferrite formation, and due to that you stabilize austenite, and the austenite can be transformed to martensite upon cooling to room temperature. So this is the microstructure what we talked about before hot stamping, and this is after hot stamping. So you start with an ferritic bainitic microstructure, you end up with fully martensitic microstructure. Okay, so the strength increases significantly, and you don't really compromise in formability, because you are forming at high temperature in austenitic region where material softens significantly. in the austenitic region, and you form it, you make the component, you cool it, and you form a fully martensitic microstructure, and due to that the strength of the component increases significantly. Okay, so this is the properties after before and after forming, and you start with the say ferritic microstructure. You have a yield strength about 300 MPa and UTS about say 450. That is what we saw in a previous in the banana diagram as well. It's a simple mild steel. Okay, and after forming, you see UTS, it went up to 1500 MPa because of the formation of complete martensitic microstructure in the component. Okay, so we will see in the detail when you look at the weldability of these steels, how the properties are affected. Okay, so to summarize this class, so we looked at the heat treatments that are needed to generate a dual phase microstructures, the role of carbon partitioning during intercritical annealing, and how the carbon partitioning to the austenite can lead to martensite formation. Okay, and then we move on to trip steel microstructure, how we get the three phase microstructures, ferrite, carbide free bainite, and the retained austenite containing microstructures where we suppress hematite formation to enrich the austenite, and because of the carbon enrichment the transmission of austenite to bainite ceases incompletely when the austenite carbon concentration reaches critical values known as T0 or allotropic phase boundary, and this boundary is defined by the carbon concentration at a given temperature where the Gibbs energies of ferrite and austenite becomes equal, and upon this concentration of austenite, the austenite can only transform to any other phase by diffusion-less manner. Okay, therefore, it has to transform to martensite. But what we do, because of the enrichment, your MS and MF temperature decreases significantly. MF goes below room temperature. So therefore, we stabilize the austenite which is untransformed during this isothermal bainitic holding as a retained austenite room temperature. Okay, so now and because of this special heat treatment, we have a three phase microstructures. Generally, we have a ferrite, carbide free bainite or bainitic ferrite, and the retained austenite. And we moved on to a third steel, which is hot stamping, and we looked at why hot stamping, why we have to deform at higher temperatures. We looked at what is the advantage of deforming or stamping in the austenitic region, and what is the role of alloying element, especially boron, to obtain a complete microstructure, complete martensitic microstructure. Apart from that, we also looked at the role of silicon, aluminum, and phosphorus in trip heat treatment.